Okay, so in lecture 8, we will briefly discuss about transfer learning, and we're going to move on to some case studies of the convolutional neural networks. So what is transfer learning? We would like to train a model with small amount of data. Then what should we do? We will briefly talk about the pre-training and fine-tuning, which you're going to hear a lot when you read machine learning papers, especially in computer vision. Then it will be followed by the CNN case studies, AlexNet, VGG, GoogleNet, and ResNet. And actually, GoogleNet has multiple versions. So we are going to cover these models today and next lecture. So transfer learning. So we have seen these slides before. We stack multiple convolutional layers from the low level, mid level, and high level. And at the end, we have some trainable classifier. So by doing this, we map this image, the pixel values, to the class labels like cat, dog, frog, horse, and so on. And we have seen that the lowest layer learns very primitive patterns like these color change or some edges or just single colors or some shapes like circles, very primitive ingredients to form the mid-level features. And mid-level features are properly combining these lower-level features to represent some more complex patterns that are useful for us to classify the images of all of these classes. And higher level features combine the lower level features in general to learn some most important patterns that is useful for us to classify the images in the data set. So that's how we use the deep neural networks to classify the images. That's what we've done so far, right? So the classifier in the end actually maps the learned representation. So learned representation means these things to the classes. So what if we have trained this model and we have all of these layers values already trained, and we have another data set with much smaller number of examples, but we would like to classify slightly different set of classes. So in this new data set, we have very small number of training data sets. So we cannot train these complex models only with those small amount of data set efficiently and effectively. So what should we do that? Suppose we have already trained model on much larger data set with slightly different labels like this. Suppose we have all of these, then we have a classifier for cat here. So we can still use the cats in this new data set. Using that model, we can still classify them. That's what we can commonly expect because we already have trained what is cat with this previous model. But what about dish here? Dish was not in this list. So these features we have learned here are, you can see that these are more like animal stuff. It's not for dish or ice. So you can guess that it will be harder to classify using just this model to classify this new data set. What about this case? The entire data set is completely different. In this small data set, you have all the pictures of the aircrafts, and the classes are its specific types. So in this previous model, you may have learned what is airplane in general, but that may not be that useful here because everything is airplane anyway. And these birds-like or some animal-like features will not be very useful to classify these aircrafts. So can we use the classifier or the learned representations from another data set, and can we reuse them? And if so, how much? How much are they useful? If the distribution of the data set and the labels are exactly the same, then we can just use them right away. But if it's slightly different, then what we can do? Should we train from scratch using the new data set? Probably not, because some very lower level features like these primitive stuff are still very useful. In most data sets, these kind of edges are quite useful, right? And some simple combination of these may be still also useful. It may have some circles or some rectangles, and we may use them as a good feature for most of the data set, even if it's like a airplane specific data set like this. But after some points, the higher level features are more specific to the data set that we have trained the model. So it may become less and less useful if it goes to the higher level features. So here's the basic strategy for the transfer learning. In general, if you have a very small target data set that you'd like to classify, you might be able to find some larger data set with similar label and example space. Then you may use the transfer learning technique. So train the entire model on the larger, slightly different data set first. That is called pre-training. So it's kind of something like this. We tell the model that this is not the exact word that you are going to learn, but we have more data. So just learn about this, even if it's slightly different from what you are going to be tested. And you learn just basic stuff, just like teaching a baby to learn about the word before we teach computer science specifically. And then we remove the very last classification layer, or a little bit more layers, and freeze the beforehand, which means the primitive features it learned from the pre-training, we assume that they will be still useful. So we train only the last few layers on the small target data set, like this airplane data set. So it will reuse some lower level features like this, but still it needs to learn this classifier. And now it does not take advantage of these high level features because they will not be useful anyway. And it just uses the lower level features, and we just remove these. So if the task and target data set is similar, then you just need to retrain this classifier only, or only the top layers. And if they are more different, then you may have to retrain more layers from the top. But given that your target data set is smaller, actually training the very few top layers may not be that heavy, and small amount of data set may be enough or still okay to train those, fine-tune those models. So here's an example. Imagenet is kind of a large image data set with a variety of objects, like 1,000 classes. So you train the image classifier in general. This is called pre-training. And so you can use these deep neural networks to classify these 1,000 classes. And then suppose you have some small data set with C classes, like C is like 20 aircraft, different types. Then you freeze all of these layers. And then, sorry, this it's not a good example. Let's say this is another general image data set with C classes, with smaller number of classes. And then you just reinitialize the very last layer, and all the other feature extractors are frozen. So just take the inference of these models, using this model for your new data set, small data set. And then each of these examples in the small data set will be represented as a vector using this pre-trained model. And then you just map those vectors to the class space in the small data set using this FC or some classifier. But if you have a slightly bigger data set, or if you have data set with quite different distributions, with more difference, then you may have to train a little bit more layers below that. But you still freeze the previous parts. Especially at the very beginning, they learn some common things anyway, like edges or color change. So this is just a basic strategy of the transfer learning. So here's the summary. So if you have a pre-training data set with similar data set, similar larger data set available, or no similar data set available, and if you would like to target some small data set or large data set, here's the strategy. If you have large target data set, then it's okay. You can actually just use that data. So if you can't find similar other data set, which is larger, then you may just fine-tune, you may just actually train on your target data set only. But if you would like to take advantage of the even larger data set pre-training, you actually do that and then fine-tune more layers of that because you have larger target data set. But if the pre-training data set is quite similar, then it's the best case. You can just reuse them and you just fine-tune the very last few layers, like the classifier. But if the target data is small, then you have some problem. If you are lucky to have some similar data set in larger scale, then you pre-train on that large data set, and then you fine-tune only the very last classifier. Suppose you use a linear classifier because your target data set is too small, so you cannot fine-tune much more layers. So actually, you trust the features or the patterns you learned from the larger different data sets and just reuse that because you have small data. This is the hardest case where you have small target data and you cannot find the similar larger data set. In a lot of practical applications, you will encounter this kind of situation. Actually, many students in this class are coming from medical domain or biology. There, actually, you have very small number of images available, like the X-rays from the patients. It's just number of like an order of hundreds or thousands. But we have like millions or billions of images available for general image data sets. But kind of medical data is usually the scale is smaller. But you would like to discover some patterns in them, then what should you do that? You can use the Imagenet or some images you crawl in Google. Doesn't work because it's not similar. X-ray is very, very different from just regular images we can just download from the internet, right? So in this case, pre-training may not have that much, unfortunately. So yeah, I don't know. In that case, transfer learning is not a solution, basically. So it just say that you may try some simple classifier from different strategies, but from different stages. Yeah, it's not an answer. I mean, in that case, yeah, it's no good answer. I mean, just you need more data, unfortunately. So why do we do the transfer learning? So that was a hot potato in deep learning because theoretically speaking, we should be able to learn the same quality of the model if we have just the target data and that training the model enough, then it should be reaching to what we can get from the pre-trained model because it was trained on different distribution of the data points. So this paper actually did some experiments like that. So it starts with Imagenet pre-trained model, which is this gray line. And they have trained only on the target data set, which is this purple line. And at the beginning, the pre-trained model performs much better. And before this paper, people have just trained up to this point, and they concluded that Imagenet pre-training is kind of essential to get this high performance. But what happens after that? So they actually continued their training up to this like 10 to the 5. So it's like 500,000 iterations. Then they found out that they actually reached to the same point. They converged to the same point. So they kind of concluded that Imagenet pre-training is not necessary if you have enough computing power and data set. But Imagenet pre-training may be useful if you would like to finish it quickly and if you don't need the very last performance that it can achieve. It's very similar here before just 언제부터 끊겼어요? 아, 진짜? 여기 채팅에다 써주시면 제가 이걸로는 보고 있는데. Sorry, I was disconnected. So popular. Wow. Sorry about that. What is the last one you actually told me? Can you hear me now? Uh-oh. Can you hear me now? Okay, sorry about that. I hate SKT. I'm using the tethering using my phone because the GSDS internet sucks. So I'm actually using my personal data plan, but actually SKT sucks as well. Sorry about that. Yeah, so I guess you missed about 10 minutes. So can you tell me which slides was the last one you actually I was on?
It was slide 11.
11. Okay, it's not as bad as I said. Okay, let's finish the 11 and 12 and we can finish there. So yeah, sorry. So here, yeah, this is a paper from Facebook that do we really need to train a model, pre-train a model on Imagenet or larger image data set, or can we just train on the target data set? And the conclusion before this paper was like this. Starting from the Imagenet pre-trained model, actually the performance was like this gray line. And if we just train...
교수님, 그
네.
화면이 안 나와 있어서 공유가.
이것도 안 돼 있구나.
네, 이제 보입니다. 네.
Yeah, sorry again. So, yeah, we pre-train a model to, we pre-train a model on ImageNet or larger image data set, and then we fine-tune on our target data set. That's the strategy with this green, gray line here. So we start from the higher accuracy and it gets better quickly. But if we just train from the scratch, then it follows this purple line. So conclusion before this paper was like that. People just tried up to this point, and they kind of concluded that we can get better results when we pre-train on the large data set like ImageNet. So it's kind of required to pre-train on larger data set to get a great performance. But is it really the case? So these guys actually just trained further up to like actually 500,000 iterations to see if where they are actually converged to. And they found out that actually they converge to the same point if they train from scratch, but with enough number of iterations. So here, they concluded that if they have enough computing power and data set, then the pre-training may not be necessary eventually, but pre-trained on ImageNet actually helps to converge faster. So if you'd like to train a model much quickly, and if you don't need that very fine performance improvement at the end, actually you can just train on pre-train on the large data set and just use and just fine tune on your target data set with just few additional layers. So the conclusion with this paper was that the pre-training may not be needed if you have enough data set and enough computing power, but usually it's a good strategy that you can actually, you lose nothing because you can just use the pre-trained model and starting from there. So here's what the strategy you are going to follow. If you have a target data set of interests, but it has just small number of images, like less than 1 million, then you can actually start pre-training on large data set like Imagenet or even larger data set than that to pre-train your model. And then starting from there, you can actually fine-tune on your target data set. But actually training on this large-scale data set is extremely time-consuming, and it requires a lot of computing power. So you don't actually have to do that again, because a lot of people already have done that. And company like Google or Facebook or Microsoft, they already have trained their pre-trained models, and they have released it, and it's publicly available. So you don't actually have to redo that. You just download the pre-trained model and fine-tune with your target data set, or just run the inference to extract the feature representation of those images, and just start from there. You can just fine-tune your on your target data set. So I have linked the TensorFlow and the PyTorch, so you can actually browse the models available there, and you can start to extract your features on your target data set. Sorry about the disconnection issues. So I wanted to start this case studies today, but yeah, maybe we can stop here, and we're going to actually see the CNN case studies in the next lecture. Okay. Thanks for attending today, and you can ask questions now. And if you are uncomfortable with English, you can ask questions in Korean.